Okay, this is going to be the second part of the Bohr model vodcast, and what we're going to look at is how we take those three equations that we talked about and how do we apply that to the Bohr model of the atom. So if you remember from the first vodcast, what we did was we had three equations. We had E is equal to H times nu, and then we had nu is equal to C over lambda, and we had lambda is equal to C over nu. Remember, E stands for energy, H is Planck's constant, which is simply a value, and the value is 6.63 times 10 to the negative 34th, and its units are joules times seconds. Nu stands for frequency, and its units are inverse seconds. C stands for the speed of light, and its value is 3 times 10 to the 8th, and its units are meters per second. And lambda, we said, stands for wavelength, and its units are going to be in meters. Now, oftentimes our wavelengths are given in nanometers, which we'll have to convert to meters, but we'll address that in a moment. So anyway, what we want to do is we want to talk about how these three equations are used in the Bohr model of the atom. Now, if you remember from our previous podcast, the Bohr model has the nucleus at the center, and it has our energy levels around the nucleus. In between each of those energy levels is a certain amount of energy. And what we said was if you put some energy into the atom, in other words, if you put the atom over a Bunsen burner or put some sort of charge into the atom, what happens is those electrons jump up to higher energy levels. Well, when they do that, as soon as they do that, they're going to fall back down to their what we refer to as the ground state. And when they do that, they're going to release the amount of energy that was put into them to put them up to that level. So for example, what we can do is look at these different levels. So let's just assume that the nucleus is at this level here, and we have our first energy level, second energy level, third, fourth, etc. So if we have an electron, say, in the first energy level, and what we do is we put some energy into it and we promote it up to the third energy level. It's now in what we refer to as the excited state. So it is in the excited state. When that electron now falls back down to the first energy level, which it wants to do, that first energy level is what we refer to as the ground state. In other words, it's the state of lowest energy. The electron is going to release that amount of energy. So we go back to our equation, energy is equal to H times nu. Well, if we know the amount of energy it takes, or the amount of energy it will release when it falls, we can then calculate frequency by rearranging that equation to be frequency is equal to E over H. Once we know the frequency of that light, what we can do then is calculate wavelength, because we know that wavelength is equal to C over nu. That wavelength of light then we can apply to the electromagnetic spectrum, like we talked about in the first vodcast, and we can see what color of light the electron emits. So for example, if you've got a couple of electrons present here and you promote one up to the second level, you promote one up to the third level, maybe one from the second level goes up to the fifth level, etc., those are all going to fall back down and release specific energies of light, which have specific frequencies, which all have specific wavelengths. So these different wavelengths of light will be visible if they're in the visible region. So what's going to happen then is as these electrons fall from different levels, and this is a little bit difficult to read, that says wavelength, so that's your wavelength of light here. As these electrons fall from the different levels, they're going to emit certain energies corresponding to certain frequencies, corresponding to certain wavelengths. So for example, and this is a little bit difficult to read, what this spectrum here represents is a specific atom, and in this case it's mercury. So when its electrons fall down, it's going to release energy of certain wavelengths of light corresponding to that wavelength, that wavelength, that wavelength, and that wavelength. So Mercury's atomic structure is such that when its electrons fall back down to the ground state, they release light at those specific wavelengths. So each atom, sodium, hydrogen, helium, for example, have different atomic structures. So as their electrons fall from different levels, they will release different wavelengths of light, giving us what we refer to as the fingerprint of the atom. So for example, let's say you have an electron fall from the third energy level down to the first, and it gave off 3.45 times 10 to the negative 19th joules of energy. So its energy is equal to 3.45 times 10 to the negative 19th joules. What we can do then is we can calculate its frequency by rearranging the equation. Frequency is equal to 8 or E over H. So let's do that. 3.45 times 10 to the negative 19th joules. And we're going to put that over Planck's constant, 6.63 times 10 to the negative 34th joules. And if we do the math there, we'll take 3.45 times 10 to the negative 19th divided by 6.63 times 10 to the negative 34th. We're going to get 5.2 times 10 to the 14th, and that's frequency, so it's going to be inverse seconds. Well, what we're going to do then is calculate our wavelength of light that would correspond to by taking C over nu, which is 3 times 10 to the 8th meters per second divided by the frequency that we just calculated, 5.2 times 10 to the 14th inverse seconds. And when we do that, we get 5.76. We get 5.76 times 10 to the negative 7th meters. Now, if we want to look at that on a electromagnetic scale, usually that's given in nanometers. So if we convert that to nanometers, we would get 576 nanometers, with which, if you looked on the scale, would correspond roughly to orange light. So if you were looking back at your electromagnetic spectra or your emission spectra for this particular atom, it would have a wavelength roughly in that region, which corresponds to 500 nanometers, which would correspond to orange light. So just to review, each atom or each element has a specific atomic structure, and that atomic structure will have electrons in different levels which can fall down to the ground state after they're excited, releasing a certain amount of energy of light. That energy corresponds to a certain frequency, which corresponds to a certain wavelength. So if the particular element has multiple electrons fall from multiple levels, it will release multiple colors of light, giving it its particular emission spectra, which is the fingerprint of that atom.